Hello, and welcome to your software demonstration of PCDMIS 2016. My name is Colin Sumithra-Rachi, and I'm an applications engineer from the Irving, Texas office. Today we're demonstrating PCDMIS 2016, which is the enterprise metrology solution of Hexagon Manufacturing Intelligence. PCDMIS supports a wide range of measurement machine configurations and device types, from traditional CMMs to portable devices and even machine tools. Today's demonstration will simulate a bridge CMM inspection of a common demo block, and we'd like to highlight some of the advanced techniques that let a trained programmer quickly create a measurement routine for part inspection. Here you can see that my potential customer has indicated for me what dimensions he requires CMM inspection on. Traditional bubble print drawing. So let's focus on how we would capture that data with PCDMIS. If you haven't seen PCDMIS before, I'll give you a brief tour. Over here on the left is our edit window. Contained within are the commands that make up a PCDMIS measurement routine. Here on the right is our graphic display window. Any 3D CAD data and any features we create will show up over here. And then up at the top, of course, we have our menu tree and two toolbars that put some favorite commands from that menu tree right at our fingertips. The first command we're going to use our toolbar for is to import our customer's IGES model. CAD has always been an integral part of PCDMIS. With CAD data, designers can embed their inspection routines into a model. CMM programmers can develop our inspection routines, and our reports can even include the CAD data for easy interpretation. So in this example, you can see that my customer has given me a model in IGES format, which I'll process and convert. And you can also see some of the other formats that PCDMIS is capable of importing right here. SolidWorks, STEP, Unigraphics, Inventor, AutoCAD, some of the most popular. Now that my model is imported, let me arrange it for easy use. We'll spin it, we'll resize it, and if I need to do anything stylistic, like change the edges, or wireframe or solid, I could even insert the model of a machine, which I'll do later to check to see that my simulation fits within a machine's volume. Once my model's been imported, the next step is to activate a clearance queue. This sets a region in which our probe will not run during CMM operation. If you have any extra fixturing that's not shown on your CAD model, you can resize your clearance cube to account for it. With the creation of the clearance cube, I can move on to making features wherever I need to all over the part, and let the software create the intermediate moves. The drawing indicates that I need a plane on the top. I can hold down Shift and left click, a circle, and a circle as my alignment datums, and we can see them show up in the edit window. When I use the Quick Align button, you can see that PCDMIS creates a manual alignment from those features, as well as a DCC alignment. And if I want to up the number of hits to increase the quality of my DCC alignment, I can simply go in the edit window, we'll turn off the tags, and I can start changing aspects of my plane1.dcc, which also happens to be database. For instance, maybe I want 4 hits, each on 3 rows, and I want them to be 1.5 millimeters away from every edge. So you can see, instead of having to set every hit ourselves, we can let the computer handle it for us. And that looks like a pretty safe hit pattern for my plane. For each of the circles, rather than have them be a probe circle, I can change them from being a probe circle to a scan circle. And I can let the software, by specifying my size tolerance, location tolerance, and form tolerance, as well as surface type, we can let the software automatically set the point density, the scan speed, acceleration, and offset force, so the user doesn't have to. And I'll make the same change to this circle, since it's already been created. Wonderful. My alignment's now complete, and we can refer to the drawing and start making the features we need to satisfy the various callouts. So let's go back to our drawing. Here you can see on sheet 3 of 6, section D4, callout number 1 is defined as the true position of the top bolt hole pattern as shown. I've made some of the features we need already. Datum's A, datum's D, but I haven't made datum B or the bolt hole pattern itself. So let's take care of that before we make our dimension. If I use quick features by holding down Shift and creating the plane, it'll have the same parameters as datum A, with one exception. PCDMIS realizes that this is not the appropriate tip angle to use. We've got 2 eligible tip angles, and I'll pick the second. Plane 6 is now created, and it's preceded by the tip angle. I'll rename plane 6 to be datum B. Similarly, if I choose to create a circle in the 12 o'clock hole, I may want it as a probe circle with 16 hits or 12 hits, but in the time that it takes me to make 12 hits, I could have scanned 120 hits very easily without having to set all these advanced settings. So getting that amount of data in a short time is what makes scanning so powerful. When I go to create this bolt hole, PCDMIS will demand another tip change. And the first bolt hole was created. Of course, I could hold down Shift and create more features, as you guys have seen. But if I want to show a different method, let me highlight these and use my delete button. I can copy bolt hole 1, use the pattern button to say every 45 degrees, 7 times, paste, but with a pattern. The goal should be to make your measurement routine with the least amount of work possible. Sometimes that's going to be using quick features to create features quickly from the CAD model. Other times it may be more expedient to use copy and paste pattern to get the features you need. Let's hide our tags. Now it's time to make our dimension so we finally have something to show on our report. The power of PCDMIS's exact measured functions is that a user doesn't have to be a GD&T expert. All he needs to do is to simply make his preview look exactly as it does on the customer drawing, and PCDMIS does the work with the GD&T. Since I've already made my features, let's identify them as datums. And now we're free to use them in the feature control frame. We want the true position of the entire bolt hole pattern. Comparison. That looks right to me. And you can see the dimension has been added to the report. PCDMIS first calculates the size of each of the bolt holes because, of course, their true position is being calculated at maximum material condition. So we calculate the size to see if there's any bonus. and the bonus gets added to the position, which you can see numerically, and there's also a nice gun sight where we would be able to see the position of the holes within their radio tolerance zone for both the top segment of the feature control frame and the bottom segment. If there was any datum shift allowed, because datum D was also at max, it would be recorded right here, as the entire pattern could slide in an attempt to fit. And finally, there is the bilateral tolerance right there if a customer prefers to see it in XYZ rather than true position. Since I don't, I'm just going to hide those labels. And that's everything we need for true position. Let's take a look at our drawing and handle the next callout. And you'll see that this is the pattern we follow. It's drawing driven. We locate the information we want to capture, we create the critical features, and we add it to the report by building the appropriate dimension. Let's go find what callout number 2 is. Callout number 2 is the true position of the side bolt hole pattern. So again, we've already got datum A, we've already got datum B, we need to create datum C and the bolt holes themselves. So since I'm aimed in this direction, we'll simply create datum C. It requires a tip change, no problem. There's the tip change and the freshly renamed datum C. And since I created the top bolt hole pattern with scans, and I'd rather not change anything, we can create the side holes just by holding down Shift. A tip change will be required for the first one. And they'll be inspected in the exact order that I clicked, and that is therefore showing up right here. Now that all my features are created, I'm free to create my true position. So the drawing stated it's the true position of all 8 of them, plus tolerance of 25 to minus 15, 400 thou at max to CBA. Datum C is definitely a datum. My datum reference frame is set. 5 minus 15. Looks correct to me. And our second feature control frame is created. On to callout number 3. Callout number 3 seems to be the perpendicularity of datum C to datums A and B. I believe I've created all those already, so I can get away with just making the dimension this time. There is my perpendicularity dimension. I'm interested in datum C's perpendicularity to datums A and B. And I've forgotten my tolerance. You can see how, in a way, I'm building my report in real time. As my dimensions show up, they populate my report. Moving on to callout number 4. Callout number 4 appears to be the parallelism of the right side to the already created datum C. Let's hide our tags again. There we have plane 8. and we have everything we need to build the parallelism convention. It's plane 8's parallelism to datum C. And finally, datum callout number 5, Callout number 5 seems to be the circularity of the already scanned datum D. And since we've made that feature before, there's no reason to recreate it. Circularity of datum D. Nominally, my report is complete. Now I finally have the report I need with the results I need inside of it. So I can focus on optimizing my PCDMIS program in an attempt to get more parts across my CMM every day. Those of you who are experienced CMM programmers have probably seen that I've been programming pretty indiscriminately. Some features on the left side of the part, then some features on the right side of the part, on the front, on the back. This is because I knew I had PCDMIS Path Optimizer in my back pocket this whole time. Let me show you how it works. So we'll activate our clearance queue and show the path lines to simulate what my PCDMIS probe is doing inside of my measurement routine. Once those path lines are shown, I can use the Path Optimizer to say, reorder all of my tip changes and features to try to get a more efficient program. And it looks like I can be 31.7% shorter. And we'll show the new path. Now that path optimization has taken place, two things have happened. Firstly, the number of tip changes in the program have been minimized. Secondly, the order of features has been optimized, resulting in the minimal amount of probe movement throughout the program, shown in the path lines. The next step is to see if any of these path lines take us through the CAD model itself. So we will use collision detection to check. And you'll see the virtual probe moving in the prescribed paths around the part. Any collisions will show up in the collision list. Looks like no collisions have been detected. If any were predicted, then we would see them in the list, and the corresponding path would show up as red, and we could take the appropriate steps at that point. Now we feel safe running our part. Here we've finished developing our PCDMIS measurement routine, we've optimized it, and we've checked for collision detection. So now it's time to go focus on the report. Throughout this demonstration, we have been working in text-only mode, and it's very useful for demonstrating the raw data, but there's a few other built-in options that are worth noting. The text and CAD template can be very useful when a customer doesn't have a bubble print, but he wants the most possible textual information. As you can see, all the same information is there in the text-only report, except now we've got editable tags that directly point to the inspected feature. There's also the CAD-only mode in portrait or landscape. This more visual template is useful when less information is required, like in a meeting or PowerPoint. Of course, these CAD graphics are fully editable, as are the labels. You would simply set it up as you wish and print out your PDF. Should your part need a traveler document as it moves around your facility, maybe the PPAP template will be right for you. And there's also the text in CAD, which you've seen already, but it's a variation that shows only the out of tolerance fields. Since I'm working with a perfect CAD model, everything is in tolerance, and my report is of course empty. And also a plain text. If that's what your downstream customer requires. Lastly, the inspection report editor allows a PCDMIS user to develop the templates that they need and create custom reports. Now that our program has been optimized and we have the report we need, it's time to put our part on the CMM and start getting those results. This has been Hexagon Manufacturing Intelligence's presentation of PCDMIS 2016. I'm Colin Simitfaraji. Thank you very much for your time and have a nice night.